Hi, my name is Hassan, and I'm presenting our paper titled Making the Most of Parallel Composition and Differential Privacy. It's a joint work with John, Gianpaolo, Serene, Serge, and Paul. And the problem we are looking at is the problem of answering queries on a sensitive dataset through a differentially private mechanism. And the goal is to maximize the number of queries that can be answered under a fixed global privacy loss. And the idea is to avoid wasting the privacy budget. A simplest example of that would be to avoid answering the same query multiple times with different noise. So under basic composition of differential privacy, answering T queries consumes T epsilon budget. This is not optimal, and there have been various relaxations of differential privacy in order to find a tighter composition. Most of these works are on sequential composition, and less focus has been given to another form of composition called parallel composition. So informally, this means that two mechanisms are composed in parallel if they work on disjoint subdomains. In this case, the privacy loss is only maximum of the two. And the intuition behind that is that individual can only be in one of these two data subdomains. So if we have two queries which are on the two different subdomains, and each having a privacy budget of epsilon, then under basic composition, the privacy loss is bounded by 2 epsilon, but parallel composition gives us a tighter bound, which is only epsilon in this case. So we can squeeze more out of the privacy budget if we use parallel composition. So the question then is that if we're given a number of queries T, each with a different privacy budget, and a fixed DP mechanism, how do we find out if any subset composes in parallel? In order to answer that question, we define the notion of maximum overlap, which is defined in terms of query coverage. So for a single query, we define its coverage as all the domain points, which if removed would change the answer to that query. And likewise, we can define the coverage of a set of queries as the intersection of the individual coverages. The maximum overlap is then the maximum budget consumption by any subset of queries that overlap. So optimal composition would then be related to the maximum overlap in the sense that the privacy loss would be exactly the maximum overlap, and the rest of the queries will be composing in parallel. So how do we compute that? A naive solution would look at all the possible subset of queries to check if they overlap. And there are two different parameters which affect the complexity. One is the number of queries, because we need to check all possible subsets. The other one is the domain size, which is exponential in the number of attributes. And the reason for that is, in order to check if queries overlap, we need to go through all the domain points in the naive way. And notice that the domain points is different from the actual data points. The domain points covers all possible data points that there could be. So in order to tame this complexity, we focus on a subset of queries called predicate queries. These are defined as conjunctions of predicates on individual attributes. So Q1 to Q3 are examples of predicate queries. On the other hand, the query says postcode A or native equals N is not a predicate query because it's actually a disjunction. And the reason to use predicate queries is that we can check if any two queries are disjoint by looking at the predicates individually. If on any attribute the predicates are disjoint, then the queries are disjoint, as in this case. Unfortunately, even if we can check pairwise whether queries overlap, the problem remains NP hard, because even if they pairwise overlap, the joint coverage might be empty. And this is not surprising. An instance of this problem has been shown to be NP hard, which is defined in terms of finding the L1 sensitivity of a subset of queries. And in our paper, we also show that the more general problem of maximum overlap is NP complete. We're calling it more general because it covers DP mechanisms which are not defined in terms of L1 sensitivity, for example, the Gaussian mechanism. So if this is NP complete, what can we do? Our idea is to formulate the problem in terms of graphs. So one way would be to formulate it in terms of a hypergraph. So each node in the hypergraph is a query, and a hyperedge is any subset of queries that has a coverage that is non-empty. Then we get the maximum overlap readily as the cardinality as the hyperedge with the largest cardinality. Problem is that this has exponential time to construct this hypergraph. So instead, we focus on the query graph. Each node again is a query, and there's an edge between two nodes if they overlap. This only takes t squared time to construct, but we don't get maximum overlap readily. Instead, we are going to link properties of this graph to maximum overlap. So here's an example of the query graph formulation. We are given 6 queries here. On the top here, we have the query graph, and the bottom we have a hypergraph. The three queries here have a joint coverage that is not empty, and this is indicated by this hyperedge shaded in gray. So which problems could then be related to maximum overlap? One of them is maximum click, which is defined as the size of the largest complete subgraph. The problem is, in this case, we need to use an exact algorithm because any approximate algorithm may underestimate the click number, which could in turn be less than the maximum overlap, which could be a privacy breach. Our proposal is instead to use the chromatic number. And the advantage here is that we can use approximate algorithms for that because it's a minimization problem. And hence, any approximation would be higher than the maximum overlap, and no privacy leakage would result. Even though these two problems are still NP complete, they have been studied very extensively, and hence the algorithm might be efficient in practice. So in order to check that, we have our experimental setup. We are checking the efficiency of the algorithms in terms of 2 parameters in general, the domain size and the number of queries. And we also have a timeout because we are looking at online mechanism. So any query that takes more than 60 seconds is considered to have failed. In order to test utility, we look at the percentage gain if only sequential composition was applied, and we have both synthetic and real census queries. And the algorithms are exact maximum click, exact maximum overlap, and the approximate chromatic number. So the first of our results shows the feasibility of the algorithm in terms of the increasing domain size on the y-axis and the increasing number of queries. The yellow regions show those queries that were answered within the timeout of 60 seconds. And we can see that the approximate chromatic number can handle more queries than the maximum click. In terms of utility, we worked on a data set of real census queries obtained from Australian Bureau of Statistics. And we can see from this table that in almost all cases, we obtain good utility due to the maximum overlap. And this is over simple sequential composition. There are other contributions in our paper. One of them is that instead of simply defining maximum overlap as a fixed mechanism and t different queries, we can define it as the composition of t different DP mechanisms. and see if they compose in parallel. So in order to define this, we define that under the notion of F differential privacy, which is a recent notion of differential privacy characterized in terms of hypothesis testing. One of our contributions is to prove a parallel composition theorem for FTP, and also then use that to have an arbitrary optimal composition for FTP mechanisms. The reason to focus on FTP is that we can then relate all these results to other flavors of DP through the connection with FDP. There are some limitations in our current work. One of them is that we, with each new query, we need to regenerate the query graph. So instead of that, a dynamic approach which only updates the current query graph could be useful. Likewise, we could do some pre-processing before the query graph is constructed. So this could be that queries which are obviously can be obviously grouped together, could be grouped beforehand. Another thing is we have defined query overlap as a binary problem, but we could look into the extent by which queries overlap and may be able to squeeze more out of the privacy budget using that approach. And some other pointers could be to use approximation algorithm for hypergraphs instead of just looking at the query graph, or any other problem that could relate to maximum overlap for which we know some efficient algorithms in practice. So that's the end of the presentation. If you have any questions, you can email me or Paul.